Okay, today's paper is, are your reasoning models reasoning or guessing? A mechanistic analysis of hierarchical reasoning models. It's by Zuri Ren and Ziming Liu from Tsinghua University and the Shanghai TG Institute.
And the premise is pretty wild. They look at hierarchical reasoning models, or HRMs, which recently just crushed LLMs on the Sudoku-Extreme benchmark. But, and this is a big but, the authors found what they call a fixed point violation.
Which
It
means
means these models fail on ridiculously simple puzzles, like a grid with just one number missing. They can't stop processing. They just keep going until the correct answer gets corrupted.
so they overthink it into a wrong answer. And the reason for this is something called rival attractors.
Exactly. The model's internal space, its latent space, is just filled with these traps, these local minima. So the model isn't refining an answer. It's basically just guessing which attractor to fall into when it starts.
And they proved this by looking at the model's learning dynamics, what they call grokking dynamics.
Right. The loss curve isn't a smooth slope down. It stays completely flat, super high, and then bam, it drops to zero in a single step.
That's not learning, that's like winning the lottery.
It's a lottery win. So the authors just leaned into it, they stopped trying to make the model reason, and instead just got better at guessing.
Which led to the augmented HRM, using things like data mixing, input perturbation, and model bootstrapping.
And the final result. Accuracy on Sudoku-Extreme jumped from 54.5% all the way up to 96.9%. State of the art.
Okay, so that's the 1-minute summary. Let's untack this, because this paper is kind of an attack on our ideas about system 2 thinking in AI.
It really is.
We all love the idea of models that can think for longer, take their time. But Ren and Liu are basically asking us to check our assumptions. Is the model actually thinking in that time, or is it just spinning a roulette wheel?
It's a brutal takedown of that whole refinement story we tell ourselves. In ML, there's this idea that recursion is always good, that if you loop a model on itself 10 times, step 10 is somehow smarter or more refined than step 5.
Right.
This paper just says, no. For these HRMs, step 10 might just be a random leap to a totally different spot in the latent space.
So before we get to the rival attractors, which, by the way, is an amazing name for a band, let's set up the architecture, because we're not talking about chain of thought here. This isn't GPT-4 writing out its steps.
No, absolutely not. We all get chain of thought right.
Yeah.
It's auto-regressive. It spits out a token, reads it, spits out the next one. That all happens in text space.
It's thinking out loud.
Exactly. HRMs are different. They work entirely in the latent space. So they take the problem, they embed it into this high-dimensional vector, and then they just pass that vector through a reasoning module again and again and again.
Yeah.
It's thinking without talking.
And this is where the trouble starts, right? With this training hack they use to make it efficient. Deep supervision with one-step gradient.
Yeah, and this is standard practice, to be fair. If you tried to do full backpropagation through time, your compute costs would explode. It scales quadratically with the number of steps.
Mm-hmm.
That's O of t squared. It's just too expensive.
So they cut corners.
They detach the gradient. So at each step, they calculate the loss, they update the weights, but they don't send that gradient signal all the way back to the previous steps. It brings the cost down to linear time, O of t.
But there's no free lunch in deep learning. When you detach that gradient, you're breaking the chain of causality between the steps.
You are. And to make that, mathematically, you have to lean on this thing called the fixed point property.
Mm-hmm.
You have to assume that once the model finds the answer, let's call it Z star, then feeding it back in won't change it. F of Z star has to equal Z star.
You're assuming the model knows when to stop, that it finds the answer, and then
Yeah.
it just sits still. It's stable.
Yes. And that is the assumption that just completely falls apart. Because they detached the gradient, they never actually taught the model to be stable. They only taught it how to get the answer at one specific step in the chain. They never punished it for wandering away later.
Which they discovered with what has to be my favorite unit test of the year. They train this thing on Sudoku-Extreme, puzzles that are incredibly difficult. It learns to solve them. And then they give it a simple puzzle.
A completely solved grid with one single cell empty.
And what happens?
It's a disaster.
Yeah.
The one cell disaster, the human solves it in a second, the HRM, it just tanks. We're talking success rates dropping to 0 in some cases.
Okay, walk me through that. What is actually happening inside the model? It sees the grid, it correctly fills in the missing, say, 5, and then...
And then the loop keeps going. The recursion is hard-coded for, 32 steps.
Yeah.
So it takes this perfect, complete solution and feeds it right back into the reasoning module. And because it was only ever trained on noisy, incomplete puzzles, It sees this perfect solution as just another problem to solve. It starts reasoning on the answer.
It overthinks it.
It literally corrupts its own work. It'll start changing numbers that were already correct because the model never learned that a solved state is a stop sign. That fixed point isn't an attractor for it. It's just like a waypoint it blew past at high speed.
I love the analogy you used before. It's like a self-driving car that's trained only on racetracks. It can go 200 miles an hour, but you ask it to park in a driveway and it just crashes into the garage. It doesn't have brakes.
That's a perfect way to put it. The one-step gradient taught it how to accelerate, but because they detached the gradient, they never installed the brakes. They never taught it how to recognize it has arrived.
So the authors see this failure, but they don't just stop there. They dig in. They do this mechanistic analysis using PCA to visualize what's happening in the latent space. What did they find in there?
They found that the latent space isn't this nice, smooth bowl where you just roll to the bottom. It's a rugged landscape, and it's filled with these things they call rival attractors.
These are the false fixed points.
Exactly. Picture them as like gravity wells, but they're in all the wrong places. So the model starts its reasoning process, and depending on where it starts, that initial random state, it might just get sucked into the nearest gravity well.
And if that's a false attractor?
It gets stuck. It converges to a wrong answer.
But what is a false attractor, actually? Is it just random noise?
No, and this is where it gets really cool, especially for any engineers listening. They actually figured out what they are. They created this heuristic, this energy function, that basically just counts the number of conflicts on the Sudoku board.
Okay, so like how many duplicate numbers in a row or a column or a box? A perfect Sudoku has an energy of 0.
Precisely. And what they found was that these false attractors correspond perfectly to local minima in this energy landscape. So imagine a Sudoku board where every single row is valid and every column is valid, but maybe one 3x3 box has 2 7s in it.
That state is almost right. It has very low energy.
Very low. It satisfies, 95% of the rules. So the model gets there, it looks around, and it sees that any small change it makes would actually increase the number of conflicts.
So it thinks it's done. It says, well, I guess this is the answer.
It's trapped. It doesn't have enough sort of momentum or thermal noise, to borrow a term from physics, to jump out of that little ditch and find the true global minimum, the actual solution.
This all connects to the grokking phenomenon they observed. I want to spend a second on this because grokking usually refers to this delayed generalization during training. But here they mean something different, right? Something happening at inference time.
Yeah, it's about the dynamics within a single forward pass. If you plot the error of the model's prediction at each step of the recursion, well, if it were really reasoning or refining, you'd expect a nice downward slope.
Like gradient descent. Step 1 is very wrong, step 10 is less wrong, step 30 is correct.
But you don't see that at all. What you see is a step function. The error is high and totally flat for, say, 29 steps. The model's just lost, it's perplexed, and then at step 30, the error drops vertically to 0.
Which implies that steps 1 through 29 were basically useless.
They weren't useless, but they weren't building a solution piece by piece. They were just searching. The model was just bouncing around the latent space until it randomly landed in the basin of attraction for the true answer.
It's like shaking a box of puzzle pieces. You shake it and nothing happens, and then all of a sudden, click, everything falls into place. The shaking wasn't deductive reasoning, it was just random perturbation.
Which is exactly why they titled the paper the way they did. Is it reasoning or is it guessing? Their argument is that this behavior is, from a mathematical standpoint, indistinguishable from a guided guessing process.
It's not a very flattering picture of the architecture. We want to think these models are building these elegant logical chains. But if the whole process is just start somewhere random, see if you get stuck, and hope you get lucky, that's just a search algorithm, not a reasoning engine.
Right.
But I have to push back a little here. The model does end up with 96% accuracy. At the end of the day, does it really matter if we call it guessing or reasoning? I mean, isn't a lot of human intuition just a form of high-speed pattern matching? Sometimes I just see the answer to a puzzle, I don't deduce it. Why is this distinction so important?
I think it matters for reliability. If it's a true reasoning process, you can trust the intermediate steps. You can, in theory, audit its logic. But if it's just guessing, it's brittle. It's vulnerable to failing catastrophically when it sees something slightly out of distribution.
Like the simple puzzle failure.
Exactly. A guesser is brittle. A reasoner is robust. That's the key difference.
That makes sense. Okay, so the authors basically embrace this guesser identity. They decide, if it's a slot machine, let's just rig the odds in our favor. This is where augmented HRM comes in.
Yeah, they stop trying to fight the model's nature, and they start exploiting it. They have three main fixes. The first one directly targets that stability problem, data augmentation.
This is the teach the self-driving car how to part solution.
It's that simple. They just start mixing in simplified puzzles into the training data, puzzles that are already partially or even fully solved.
So the model finally learns that if it sees a correct solution, the right thing to do is nothing. The gradient should be 0. Don't touch it.
Right. It forces the model to learn the identity function. F of z should equal z if z is already correct. This stabilizes the whole process. That drifting behavior just vanishes.
Okay, so that fixes the stability. But the really big accuracy jump comes from the second strategy, input perturbation. And this one exploits a classic weakness of neural nets, which is symmetry.
Oh yeah, this is a deep cut for the engineers out there. You know, a convolutional neural net has translation and variance kind of baked in, but a standard transformer, or an HRM, doesn't have Sudoku invariance.
Meaning if I take a valid Sudoku puzzle and I swap row 1 with row 2, it's still valid Sudoku. The logic is identical, but the model has no idea.
To the model, that's a completely new alien input. It lands in a totally different spot in the latent space.
So using the rival attractors theory, the idea is if my original puzzle happens to start near a false attractor and gets stuck,
maybe the permuted version of that same puzzle will start somewhere else, somewhere closer to the true solutions attractor.
It's like dropping 9 paratroopers onto the landscape instead of just 1.
That's the perfect analogy. They generate 9 different versions of the input puzzle. They relabel the numbers so all the 1s become 9s and so on. They swap rows. They rotate the grid.
You're just playing the odds. If the landscape is full of these potholes, these local minima, the chance that all 9 of your paratroopers land in a pothole is pretty low. At least one of them should land on a hill that rolls down to the right answer.
And the results were just massive. Just this strategy alone, without any retraining, boosted the accuracy by 18.7%.
Wow. Nearly 20% just from shuffling the input. I mean, that almost proves the guessing hypothesis on its own, right? The model had the ability all along. It just needed a better starting point.
It totally confirms it. The bottleneck wasn't the model's capacity. It was initialization bias. The model was smart enough. It just had to start on the right foot.
Okay, the third and final strategy is model bootstrapping. This one felt counterintuitive to me. Usually with ensembling, you train a bunch of different models, but they ensembled different checkpoints from the same training run.
Right. They took checkpoints that were separated by maybe 2,000 training steps. And your first thought is, why would you do that? The final checkpoint should be the smartest, right? Why would you ask the version of the model from 2 hours ago for its opinion?
It's like asking a teenager for financial advice when you have the adult version of them right there.
But if you think in terms of rival attractors, it makes sense. The teenager might have a different set of biases. The model's internal randomness, its guessing strategy, it shifts and drifts during training.
So a younger checkpoint might have a different map of the potholes than the final older model.
Exactly. So by letting 10 different checkpoints all vote on the answer, you're smoothing out those idiosyncratic biases. It's scaling the training randomness, and it added another 10.2% accuracy.
Okay, let's just run down the final scoreboard. The baseline HRM on Sudoku-Extreme was 54.5%. Basically a coin flip.
Add model bootstrapping, you get to 64.7%.
Add the input perturbation, the paratroopers, and that jumps to 73.2%.
And then you add the data mixing to fix the stability, and you put it all together, 96.9%.
State of the art. And they did it without adding a single parameter to the model. They treated it like the probabilistic search engine it really was, not the logician they hoped it would be.
It's a huge win for pragmatic engineering.
Yeah.
They just accepted the architecture's flaws and built a system around them.
But it does leave you with this sort of, I don't know, existential question. If what we're calling system 2 recursive thinking in these models is actually just high-dimensional guessing, what does that mean for the future? Are we building real reasoners or just faster guessers?
It really makes you look at the current AI hype with a more critical eye. You see models like DeepSeek-R1, or you hear rumors about OpenAI's next thing, and they're all about massive reasoning traces, thousands of tokens of thought before an answer.
And the immediate reaction is, wow, look at it think. It's refining its answer.
But if you apply these findings, are we sure? Are those thousands of tokens genuine logical refinement? Or is the model just generating noise to perturb its own internal state, hoping to stumble into the right answer?
If that step function loss curve holds true for LLMs, then maybe 90% of a chain of thought is just waste heat.
It could be. It suggests that just scaling up inference time compute might not be the silver bullet we think it is. If all you're doing is buying more lottery tickets, eventually the cost of the tickets is more than the prize.
And you can see the danger of this fixed point violation in AI agents, too. If I have an agent that's writing code and it finds the bug and fixes it, but I let it keep running.
It might fix the fix. It could introduce a new bug.
Right.
We actually see this with coding agents sometimes. They'll play a patch, verify it works, and then apply a second patch that undoes the first one. That's a classic stability failure.
That one-cell Sudoku test should be a standard benchmark. If your 100 billion parameter model can't look at a solved problem and just do nothing, you don't have a reasoner. You have a drift machine.
It's a call for more rigor. Don't just test your model on the hardest problems. Test it on the easiest ones, too. Can it stop itself? If the answer is no, you've got a fundamental problem.
So for a final thought, here's something to chew on. If what we're calling reasoning is really just navigating an attractor landscape, does adding more compute just build us faster guessers? Or is there a fundamental architectural change we need to move from this grokking dynamic to true step-by-step refinement?
That is the big question.
We'll link the paper. It's a fantastic read, especially the visualizations of the latent space. Seeing those attractor landscapes really drives home how fragile this whole process is.
Definitely. It's a good reminder that the optimization landscape is not a logic tree.
That's all for this episode of the AI Paper Podcast. Keep questioning your loss curves, and we will see you in the next one.